Thank you thank you very much for the introductions, and I apologize for not being able to come to Toronto because of my visa processing issue. Anyway, today I would like to tell you our recent work on multiscale perturbed gradient descent. This is based on the joint work with Yijun Wang and Umo Sisensky, which is so both of them are based in Paris. Okay, so let's me start with some background. So the motivations for introducing multiscale perturbed gradient descent is coming from the setting of optimization in supervised learning. So in theory, we start with considering population risk minimizations, where we aim to minimize expected value of certain loss functions. And these loss functions depends on some learnable parameter X here, and also dependent on the data sample Z here. And these are usually coming from some unknown distributions. And so this is the setting. But in practice, people look at, instead of looking at this problem, we look at empirical risk minimizations, because in practice, we don't really know what is the data distributions. So empirical risk minimization serves as a proxy to solve the population risk minimizations. So in this ERM, it's much simpler in the sense that you replace expected value by simply average over the data sample that you have, so training set. So here we have n data points in the training set. So typically, to solve ERM, people use gradient-based optimization algorithms, especially in deep learning, in training deep neural networks. So the simplest version is full batch GD. So GD here is gradient descent. So it is just simply a deterministic recursion of the following form. So remember, X is the parameter that we are trying to optimize. So here xk are the iterates of these recursions. So gradient descent basically use this recursion to arrive at some value or parameter. And it depends on the gradient of the loss functions of the empirical risk. So R hat here is empirical risk that we saw earlier. And eta k here is step size. So in general, it can also depends on the iteration number, but it can also be constant as well. And so for full batch, the gradient is evaluated using the full training set, Sn. And a more popular version of gradient descent is what people call mini batch with stochastic gradient descent. So this can be seen as a stochastic counterpart, where the gradient is evaluated using only a mini batch uniformly sample from the training set. So not using the full training set. This made the algorithm itself more efficient, and hence is very popular in in training deep neural networks. So so there are a line of works that try to understand gradient descent versus stochastic gradient descent from different point of view. And I think in this talk, we want to focus on generalization performance. There are other things like conversion and efficiency and so on. But in this talk, we just want to basically try to understand gradient descent at the fundamental level a little bit deeper by just focusing on generalization performance. And this is measured by looking at the generalization error, which is defined by the difference between the empirical risk and the population risk. And so there's the recent paper that shows very interesting finding that, in fact, full batch gradient descent can achieve similar generalization performance as long as certain design choices are implemented. So this basically just say that stochastic training may not be necessary for generalizations. And also the paper claimed that because people are way too obsessed with SGD, so they fine-tune the training procedure so much that SGD can outperform GD so much better. But the thing is, if you go back to GD and try to see if you can fine-tune GD, so by adding some tricks on GD, and see if you can get a performance that match the stochastic gradient descent. So this is like the motivation of this work by Jerry Payne et al. Last year. So usually what they do is that they try to use like large learning rate or oscillating learning rate schedule, or maybe they want to they add some explicit regularizer to basically mimic the beneficial effect of SGD. So this is this table basically shows a result of from their paper. So they indeed show that by adding some tricks on top of full batch gradient descent, the algorithm can somehow match the baseline SGD result. So this is for CFAR 10. So now what's up with large learning rate, right? So again, there are a series of papers that try to understand this. The main result is that contrary to the wisdom of optimization theory, using large learning rate can provide better generalization performance. So this has been observed empirically in non-convex optimization settings. And recently, there's a paper by Combe and Tao. They show that rigorously that the use of this large learning rate actually introduced certain chaotic behavior in the gradient descent dynamics, and made them convergent not to a local minimizer, but to a statistical distributions. And chaotic systems exhibit stochastic-like evolutions, right? Even though they are really deterministic by themselves. And we thought that this might be the underlying cause of the improvement in generalizations that people obtain in non-convex settings. But the thing is that trying to achieve this chaotic dynamics is actually a problem-dependent thing, and it can be quite difficult in practice. So motivated by all these lines of work, we introduce a framework that we call multiscale perturbed gradient descent. So basically, we add some perturbations to the gradient descent. And what type of perturbations? So this is a thing that we are going to talk about next. So for now, in full generality, let's consider the following deterministic fast-slow dynamical systems. So here you see that this is like a way more general system than GD, but later we are going to connect this to GD and MPGD. So this is basically here, this is a couple system of differential equations where X is depending on the parameter that you want to optimize. And then now there's also Y. So another system, which is generated by some map Ti here. And so you can see that, okay, so let me just introduce multiscale perturbed gradient descent first. So if we simply just, set some of the functions like AM to the negative gradient of the risk function, and then the BMI to this and BM2 to this, then we arrive at these equations. And you can see, so how this is different from the full batch gradient descent is that now we have additional terms in the equations for X. So these are the terms in box. So there's a term depending on V1, YK1, and then V2, YK2, where this YK, so they are basically generated by some map T. And what is this map? So these are what is V1 and V2? So these are the things that we are going to introduce next. So so basically you can think of these components in box as some sort of chaotic components that we introduce. And later we will show that this can indeed give some interesting result when we compare to simply gradient descent. So now let me tell you what T is. So here T, we take T to be the Taylor met. So the Taylor met depends on some parameter gamma here, and this is between 1/2 and 1. So Taylor met is basically a met that looks like this. And why we consider this particular met? So it has been shown again, a recent paper by Goldwald and Melbourne that in fact alpha stable loss with alpha between 1 and 2 can be generated using this map. And let me just skip this. Let me see. Yeah, I'll just skip this one. I will come back to this later. So okay. The main point is that we use this map because we can show that alpha stable loss can be generated using this map. And so here are some of the properties that we might not need later, but it's good to know. But the idea is that, so how this map can generate alpha stable loss is that because if we look at for example this term here, so if we do not properly normalize it, then usually we will not get the standard central limit theorem. But instead, if we properly normalize this term here, then we can show that this basically converges in law to some alpha stable distributions. So this is just some discussion on why we expect alpha stable loss by using this Taylor met. So here we are going to focus on MPGD with chaotic components whose limiting behavior at each time is described by this class of alpha stable law, whose characteristic function is given by this equation here. So here there are two parameters: the stability parameter alpha between 1 and 2, and the skewness parameter beta between -1 and 1. And if beta is 0, then it's symmetric, and if beta is -1 or 1, it's totally skewed. So these are the terminology that we will need later. All right. So now so we introduced the met V T just now. This is a Taylor met. And then how about V? So V, we introduce V in such a way that the observable V, because remember that V in MPGD here depends on the Y, right? Which is generated by a Taylor met. So we introduce V here in such a way that these recursions will converge to some limiting equations that can be described by SDE, driven by a Levy alpha stable noise, basically. So I mean, here are some so these are the precise procedure that we use to generate the V. But the thing is, so I mean, I don't want to go into too much technical thing here. But the thing is that if you combine this observable V with the Taylor met, and if you choose the V in this way, you can get this desired conversion of the recursion to the SDE driven by this Levy process, basically. So here are some numerical illustrations of what we just discussed. So again, right, there's a met T here, right? So it's a Taylor met, and if you just plot how this met generate the dynamics, it looks like this. So it's chaotic, right? And then if we can also plot how the observable Vy evolve. So it looks like this. And then if we plot the empirical distribution, it looks like this. And as you can see, so this indeed has some asymmetry and heavy tail. So, okay, sorry, this is actually for the distribution for the Birkhoff sum. So to be precise, with the scaling 1 over k to power gamma. So okay, so just to recap, so we have MPGD, and basically it's defined by a couple differential equations where the driving dynamics comes from iterating a Taylor map, and we choose the observable V in the MPGD. So these are the perturbations in the MPGD in such a way that when we take certain scaling limits, it can be shown to converge to a SDE driven by a Levy process. So yeah, so this is basically the thing that I'm going to talk about next. So first we study MPGD from 3 different angles. So the super diffusion limits, or what people call homogenizations, which essentially the thing that I have mentioned just now, right? How MPGD converges to certain SDE. And then I'm going to talk about generalization properties for the limiting SDE. And then why we expect this scaling to be useful by analyzing this using the lens of implicit regularizations. So first, going back to what we talked about just now. So again, the idea is that if we choose suitable scaling limits in the MPGD, so here, there's 1 over m, so m is a parameter, and then 1 over m to the power of m to the power of negative 1 over alpha. So remember, alpha is this parameter in the Taylor map. So if we sum m to infinity, basically stochastic dynamics emerges in this family of deterministic dynamical systems. Moreover, right, as I mentioned just now, the limited dynamics can be described by SDE driven by a heavy tail Levy stable process. So this is the first theorem. So again, alpha is 1, 2, and under some suitable assumptions on the coefficients A, M, and Bm. So basically, you just want to control the dependence of A and B on M. So if they are well controlled, well behaved, then we can show, okay, under further regularity conditions, that this rescale process basically converges in distributions to the solutions of the following SDE. And here, because we are dealing with SDE driven by Levy stable process, we had to be careful about the convention of stochastic integrations that we use. So this diamond here denote the Marcus integrations. I will say something about this later. And so L T here is basically Levy process with this characteristic exponent. And here we see how how alpha enters into the limiting equations. Alpha and beta enters here. So okay, so why we need Marcus integrations? Because the thing is, usually when we look at SDE driven by Brownian motions, people typically look at Ito or Sartonovich integrations. But in the case of dealing with SDE driven by processes with jumps, we have to be careful when defining the integrals. So Marcus differential equations, Marcus integration, sorry, is one way, is a way to deal with this. Basically, it involves some or infinite many jumps, and it transforms just like under usual laws of calculus. So these are the intuitions of why we use these Marcus differential equations. There are some technical details behind this, but this is what people have been using in studying this type of SDEs. Okay, since I'm running out of time, I just want to quickly go over what I have next. So if we specialize, so this theorem is pretty general, whole from this family of recursions. And if we specialize this to MPGD, we look at, so basically MPGD converges to a gradient flow. Gradient flow, there looks like this. is driven by some heavy tail DB process. And so now, okay, let me see. I have like 3 minutes. Okay, so next I want to talk about generalization properties of MPGD through this limiting SDE. The idea is that there's a recent line of work that tried to tie heavy tail process to generalizations of SGD. And we can use this same tool to study generalization properties for our MPGD. And let me just skip over all the technical thing, but the idea is that you can basically bound, you can get a bound, upper bound for the generalization error. And this bound depends on, so this is R infinity is, so the limit as rho go to infinity of this rho mutual informations. So this defined here. And so yeah, so this, and this is just a very nice way to yeah, to connect MPGD to generalize and then study MPGD to heavy tail process and then study the generalization properties. And also we can lastly we can also try to understand MPGD via the lens of implicit regularizations. So by working in the weak perturbation regime, so basically we just do some Taylor expansion about this epsilon. So epsilon is basically the amplitude of these perturbations. Then we can derive the following result. So basically we see that the average of the loss functions basically is basically the loss, the risk itself plus some terms. So in order epsilon square, there's a terms that depends on the Hessian of the loss functions. And so what this means is that, so let me just skip all this. So look at this last sentence. So this means that reducing the Hessian of the loss functions can lead to flatter minima in the landscape, and which is widely believed to associate with better generalization. So from this point of view, we see that MPGD is better than GD in this sense. And so here are some results. So we do basically perform some experiments trying to focusing on 3 different optimization tasks here. So since I don't really have a lot of time here, I will just quickly go over them. So the first one is minimizing the widening value loss. So this is basically a 2D, a loss function in 2D, but it's somehow non-trivial because if you simply use gradient descent, full batch gradient descent, then the iterate will get stuck at the initial point. So the intuition is that you should inject some noise, right, to move the iterate into other regions of the landscape. So so we show that basically, so if we use Gaussian noise, then sure you can move it around I mean the neighborhood of the initial point, but then it won't really converge to the desired minimum. But if you use MPGD, then the chaotic perturbations in the MPGD, they are enough to stir this iterate to the desired minimum. And here we also plot the Hessian of the loss functions, and we see that yeah, MPGD is basically effectively reducing the trace of the loss Hessian. And this is in agreement with what we saw earlier with this analysis of implicit regularizations. So basically it moved the solution to flatter region of the loss landscape. So this is just one, this is one of the 12 experiments. And then we also basically test the MPGD on 2 other tasks. So this is a regression task, and we saw that yeah, MPGD also gave better generalization performance compared to the baseline of full batch GD, and compared with GD with using Gaussian perturbation instead. And similarly, if you look at CFA10 classifications, so here we use, when we do this, we use the entire training data set to train the neural networks. So here we use a ResNet basically. And similarly, we can see that when compared to the baseline gradient descent and with the gradient descent using Gaussian perturbation instead, MPGD outperformed them again. So the message here is that these chaotic perturbations of MPGD, it can be potentially a useful trick to improve training in for the architectures. So to sum it out, so what we introduce here, so we introduce MPGD, so which is based on a class of slow fast deterministic dynamical systems. And the idea is that this system is in such a way that if we take the limit, certain scale limit, so the small set size limit, then it will homogenize to a limiting SDE driven by a heavy tail DB process. And then because of this, we are able to make connection to the recent theoretical links between heavy tail process and generalizations. And then we obtain a generalization bound. And basically, this generalization bound depends on the parameter alpha, right, in the Taylor-Met. And we further demonstrate why MPGD is better than GD in the sense that it basically introduced terms implicitly in an implicit way that penalize the Hessian or the loss functions. And then we also provide some experiments to show that MPGD works better than GD. As for future work, I think it will be interesting to see so how these chaotic perturbations that we introduced in MPGD interact with the noise arising from the mini batch sampling in SGD. And there are also other optimization tricks that we can add on top and then see how they interact with each other and so on. And if you want to learn all the other details, feel free to check out our paper and the code. Thank you very much for listening.